We have a number of interesting talks set up again for this part of the session, and our first speaker is going to be Riccardo Bonanno, talking again about heavy precipitation in the Mediterranean.
Thank you very much. Good morning, everybody. In this presentation, I will talk about the changes in heavy precipitation events over the Mediterranean Basin, with a particular focus on the impacts on the electro-energy system. In fact, one of the mission of our company is essentially to study the impacts of the meteorology and of climate change on the management of the electrical system and on the energy system. In this presentation in particular, we are talking about extreme events, and the focus is on extreme events. And the reason for that is essentially for the fact that it's known that in recent years, severe thunderstorms in Europe have caused losses more than €1 billion, mainly due for hail, strong gust wind, and also flash flood events. In particular, in Italy, the situation is that the first cause of outages in high voltage power line is essentially the adverse weather, as floods, wind gusts, droughts, ice formation. And secondly, we have also lightning storms during the warm season, especially in the region between the Po Valley and the Alps. So considering this point, it is clear that it's really important to study the trend of extreme events in future climate change, in particular to localize the regions that are more likely exposed to these phenomena. So this is the outline of this presentation. In particular, I will show you the dataset, the daily dataset that we used, essentially the observations and the regional climate models. Then I will show you the bias correction method that we used for the RCMs. Then I will talk about the future projection about extreme events, and finally the conclusion, also implication on the electro-energy systems. Here I show you the daily dataset. We use the RCMs coming from the CORDEX database. The resolution is 50 kilometers. In this table, I show you the dataset, the models that we used, and also the acronym that we used in these presentations. We considered both the LCP scenarios, the 4.5 and the 8.5. As regards the observations, we use the OBSGrid dataset with a resolution of 25 kilometers. The periods analyzed are the historical from 1971 to 2000, and the two future periods, the short term from 2021 to 2050, and the long term from 2071 to 2100. Here you can see the seasonal precipitation in the historical period as regards the observation, the OBS dataset, and also coming from the RCM's models that we used in this study. Generally, we can see that all the models are able to capture the main pattern, precipitation patterns over the domain, but often these models show some biases that are more or less pronounced depending on the model, depending on the region, depending also on the season considered. Obviously, we have also to take into account that in generally also the OBS dataset have some deficiencies, essentially often over the Alpine region, where we have few observations, and also we have also very complex regions from the topographical point of view. So considering this point, we applied a bias correction method for the data, for the models. In particular, we used a quantile mapping, but not a traditional quantile mapping method, because traditional quantile mapping methods are found to inflate the trends in extreme precipitation indices. So for these reasons, we opted for an alternative that is an equidistant quantile mapping method that is able to preserve the changes in quantile in precipitation simulated by the models. And so this is very important if we want to study the changes in extreme precipitation events, and so extreme percentiles. The bias correction method is summarized in 4 steps. In first one, we interpreted the RCM precipitation outputs over the OBS grid. Then we applied the equidistant quantile mapping method to each grid point in historical period. And then we perform also a cross-validation to test the goodness of the bias correction method. We computed the mean absolute error. We divided the period in 2 parts, the training period and the verification. We computed the mean absolute error to do a comparison with the observation. without the bias correction and with the bias correction. And you can see from the table that effectively the bias correction method is able to reduce the bias of the models generally for the season, and this reduction is more or less pronounced depending on the season, depending on the model considered. After that, we decided to apply the method also in the future scenario, in future climate change scenarios in the short term and the long term. And in particular, to investigate the change also of extreme precipitation events, we decided to compute several ATC CDI indices that are listed in the table with the descriptions. In particular, each index is computed on the yearly basis and then averaged over the period considered to obtain a climatological mean. We also computed the percentage variation of this index with the formula reported in the slide. And in particular, to investigate the extreme precipitation event, we decided to consider also only a few indices that are essentially the total precipitation and the length of dry periods, and also R99 total precipitation, that is a measure of intensity, the frequency of the extreme precipitation events. So in this slide, you can see an example of the percentage variation computed for each index analyzed and for all the 5 models considered in this study. And in particular, on the left on the slide, you can see a map that is a confidence map. This map is was obtained essentially counting for each grid point the number of models that give a statistically significant increase or decrease of a particular index. So in this map, you can see that generally reddish color indicate a more and more likely decrease of a particular index. On the contrary, the blue colors indicate a more and more likely increase. So the results, in this slide I show you the results for all the scenarios and all the periods for the total precipitation. And you can see a confidence map and also the average variation in percentage that we computed from the 5 models considered in this study. You can see essentially that in the short term, a decrease of total precipitation is expected in the south of Italy, less than 10%, with a confidence generally low, medium. We have a higher confidence and higher magnitude of this signal in the long term. In particular, in the RCP 4.5, you can see a decrease expected less than 10% in the central Italy, between 10 and 20% in the south, with generally medium confidence. In the RCP 8.5, we have a considerable decrease also in the north of Italy, less than 10%, between 10 and 20% in the central, and between 20 and 30% in the south of Italy. And generally here the confidence is much higher, generally medium, low, medium in the north, and medium high in the south, in the center and the south of the country. As regards, we noticed that the decrease of total precipitation, of the total precipitation is expected in the country, but considering this slide, you can see that on the contrary we have also an increase of extreme precipitation events. In particular, in the short term, you can see that generally the signal is not so strong, and also the confidence is very low, because all the model localize a different region for the increase of extreme precipitation event. But essentially, we can notice that both the scenarios agree with an increase of extreme precipitation event in the central Italy. That is more pronounced in the RCP 8.5 scenarios, whereas in the north of Italy we have an increase in northwest Italian regions as regards RCP 4.5, and in northeast as regards RCP 8.5. We have a higher confidence of the signal in the long term, in particular in the RCP 4.5, you can see an increase, a considerable increase in the region between the center and the south of Italy, and also on the northwest and in the eastern Alpine region. And in the RCP 8.5, the increase is much higher, and also the confidence is very essentially high, or very high, especially in the northeast. And the region are more or less the same, the central Italy and also the northeast. As regards the droughts period, essentially we have an increase is expected. In particular, both the scenarios, the short term, agree with an increase less than 10% in the north, between 10 and 20% in the center, the south. We have a signal that is more strong in the long term, and also the confidence is generally higher. In particular, in the RCP 4.5, an increase between 5-20% is expected in the north of Italy, between 10 and 30% in the rest part of the country. The increase is much higher in the long term as regards the RCP 8.5 scenarios. So, in conclusion, this slide has summarized the result in a qualitative way. Essentially, as regards the RCP, the R99 total precipitation, an increase is expected essentially in the central and the northeast of Italy, with a signal that is stronger and more confident, considering the long-term scenarios and also the RCP 8.5 scenarios. In particular, also an increase is expected in the northwest, but with a weaker signal and also less confident. A decrease of total precipitation is expected, and also an increase of the length of the dry periods, and the intensity and the confidence of the signal is much higher, moving from north to south of the country. As regards the implication on the electro-energy system, we can see that essentially that the increase of extreme precipitation events lead obviously to an increase of electric failures, and secondly also to a decrease of the hydroelectric power generation, essentially because, for example, in flash flood events, the management of the hydroelectric power plants could be seriously problematic. A decrease of the precipitation and an increase of the droughts lead obviously again to a decrease of hydroelectric power production due to the scarcity of water, again to problems in the thermoelectric power plants, because again the water is in this plant is used for the cooling. And as regards the future development of this work, essentially the next steps will be the coupling with the hydrogeological models to better evaluate the regions that are more exposed to the risk of flooding. This is useful in the case of if you want to plan the construction of new electrical infrastructure. The coupling with the hydrological model could be useful also for the quantification of the water availability for the hydroelectric power plants. And finally, also, if we combine the result with the temperature, we can also obtain a map of the ice overload on the overhead lines. This is a serious problem from the electrical lines, because every year this problem causes losses more than 200 million euros for the ice formation on the electrical line. So it's really important for this reason to study the region that will be more likely affected by this problem. Thank you.
Thank you, Riccardo. Very interesting perspective on impacts and especially precipitation changes. We have time for a couple of questions. One question I had in particular was, you showed a lot of damage in the beginning, which at least part of it I would have thought was due to winds. So do you have plans also to look at extreme winds and how those might play a role?
Yes, extreme winds are not investigated now, but it's quite difficult to investigate winds at that resolution of the model. We have to obviously consider model with a higher resolution, because especially in Italy, that is a very complex region from the orographical point of view, is difficult to investigate winds with a low resolution. So we have to probably also consider model at 12 kilometers to better investigate the extreme winds and the effect on the electrical grid.
Okay, yeah, there are plans to do those resolutions, so it might be useful. Might also be useful for the extreme precipitation events.
Yeah, of course, yeah.
Okay. All right, well then let's move along. Our next presenter is Changyong Park, now moving to the East Asia region.
Hello everyone. I'm Changyong from Poste, South Korea. My presentation is about multi-RCM, future projections of climate extremes over East Asia. We acknowledge contributions from CORDEX East Asia modeling teams in South Korea. Understanding past and future changes in climate extremes is fundamental due to its huge impact on human society and the ecosystem. Dynamic downscaling using regional climate model, RCM, provides a useful tool for simulating and assessing past and future climate extremes. Therefore, the demand for constant and robust projections of climate extremes is used for future projections of climate extremes has rapidly increased, especially in regional and local scales. So, this study analyzes characteristics of future projections in summer extremes of East Asia using the multi-RCMs. We use historical experiment from 1979 to 2005, present day, and RCP 8.5 scenario from 2024 to 2049, near-term future, which are available from 5 RCMs participating in the CORDEX East Asia project. These RCMs have 50 km by 50 km horizontal resolution and are driven by horizontal AO GCM. The domain region is East Asia, which is the most vulnerable region to future increase in climate extremism. The major variables are daily temperature, here at the TAS, and daily precipitation, here at the PR of boreal summer season. Projected future changes is calculated by the difference RCP 8.5 and historical experiments. A 20-year return value calculated using GEV, generalized extreme value parameters, is analyzed as an indicator of extreme intensity. Then we examine the patterns of future projection through the comparison between mean and extreme and the changes in probability distribution. Additionally, we look at relationships between model scales and future projections. As an effort to obtain more useful information on smaller scales, we carry out future projections from RCMs for selected 3 sub-regions, which have distinct characteristics of model biases from TAS and PR from our previous studies. Cold and dry bias in South Korea, and cold and wet bias in southern China, and warm and wet bias in Mongolia and northern China. From now on, I talk about projection results. As you can see, TAS and PR will increase for both mean and extremes over East Asia. And TAS has a good intermodal agreement. And then we investigate PR increase per 1 degree Celsius warming. Mean shows 3% increase, and extreme indicate 7% increase. Extreme precipitation change is consistent with enhanced moisture availability with warming over this region, which is generally consistent with global mean result. We examine the circulation changes related to precipitation change over East Asia. This figure shows the future changes of various factors in surface and low-level atmosphere. East Asian summer monsoon rain band shift to the north in near-term future. This is well consistent with sea surface temperature change. And those Pacific subtropical high is expected to expand towards the northwest. Consequently, enhanced water vapor and wind speed from warmer and more humid ocean considerably will contribute to precipitation increase. We examine the intermodal relationships of future projections between mean in x-axis and extreme in y-axis. TAS and PR show positive relationships between mean and extreme projections. Models with larger mean projection has a larger projection even in extreme. Also, future changes in mean and extreme are closely related to each other, even at grid scales, with stronger relation in TAS than PR. These figures show the comparison between model scales and future projections. A generally positive relation is found in TAS mean and extreme. Models with warmer bias has a larger projection. TAS extreme has a clearer relationships than TAS mean. In case of PR, PR represents weaker relationships than TAS mean. Nevertheless, weather models tend to predict more extreme rainfall. This figure shows the probability distributions of daily TAS over 3 sub-regions of South Korea, Southern China, Mongolia, and Northern China. Left panel shows frequency. Right panel shows intensity. And gray bar shows present day. And black bar indicates future results. For frequency, PDF shift towards warmer tasks in the future over all three sub-regions. Intensity shows increases in all percentile ranges over all three sub-regions. For PR, frequency shows the consistent increase in moderate with rainfall between 10 millimeters to 50 millimeters. And heavy rain days with more than 50 millimeters rainfall, with a slight decrease in light rain days, with less than 10 millimeter rainfall across all sub-regions. Intensity shows the intensification of rainfall over all percentiles in South Korea and southern China. This is a summary and discussion. This study examines the future changes in summer climate extreme over East Asia from 5 RCMs participating in the CORDEX East Asia project. TAS and PR over East Asia will increase for both means and extremes. Besides, increases in precipitation extreme will follow the CC relationship. And future changes in means and extreme are closely related even on grid scale. There are scale projection relationships with models with warmer bias predicting larger warming. Overall shift of distribution of daily tasks and increases in moderate heavy rainfall is shown in sub-regional analysis. This study has a limitation for using single GCM boundary pushing. For next study, we will carry out future projection study using multi-GCMs and multi-RCMs. Thank you for attention.
Thank you, Changyong. We have time for one or two questions. One thing I was wondering, you showed a connection between bias in the contemporary climate with temperature change and bias in precipitation in the contemporary climate with precipitation change. But I was wondering about correlated biases, because I would expect that there's probably a relationship between temperature and precipitation biases, which might also play a role in the change. Have you had any chance to look into that? Correlation of biases?
I do not conduct it yet.
The relationship between temperature bias and precipitation bias, that they're probably related to each other. Have you looked into any of that at all?
Yeah.
Not yet?
Not yet, yes.
Okay. Any questions? Okay, let's move along and shift to another continent now, to Southern Africa.
Hi, good morning. First, I'd like to thank the organizer for the opportunity to talk and for the financial support to be here. I want to briefly talk to you about future changes in extreme rainfall and circulation patterns over Southern Africa. Excuse me, I cannot not understand the language in here. Full screen, please. I thought visa. Can you please put on the screen? It's not showing. But basically, my talk, sorry. Yeah, it's showing here, but not there. I want to talk about the future change in extreme rainfall events and circulation patterns over Southern Africa. And the objectives of this work is to look at if the CORDEX models can simulate extreme rainfall over Southern Africa and see if the RCMs reduce bias over the driving models, the GCMs, and which I call the added value of the downscaling, and to look at the projections of extreme rainfall over Southern Africa for the end of century, and to see what are the circulation patterns, the change in circulation patterns that cause these changes. So these are the objectives. As you can see, I went through them. So to see if the models can simulate rainfall, extreme rainfall, and see if the downscaling reduce bias over the GCMs, which is added value, and to see what are the changes in extreme rainfall over Southern Africa, and see what are the changes in circulation patterns that are causing these changes. And to answer those questions, we used two RCMs from the CORDEX experiment, RCA4 and CCLM4, and these are the GCMs that were downscaled. We used these four because they were the only ones that was in common between these two GCMs, but RCA4 has around 10 ensemble members. And the observer data that we use is a GPCP and TRIM dataset for this common period. And for the methodology that we used to study the extreme event was the non-parametric approach. We used to study moderate extremes, and these are the consecutive dry days until the simply daily intensity index. We also used the parametric approach to study the rare extremes, but I'm not going to present here. And to go through the beauty contest, here we show the GPCP dataset for the total annual wet day precipitation for the period of 1997 to 2006 for GPCP and TRIM data, and the CCLM downscale era interim, and RCA4 downscale era interim, and the CCLM downscale the GCMs, and RCA4 downscale the RCMs. And the bottom one, we have the ensemble mean, which is the ensemble of these eight members. And the steeplings indicate the added value of the downscaling. So where there's steepling, we see that the downscale reduces bias over the GCM. And the top is a spatial pattern correlation between the GPCP and each downscaling. And the bottom one is the pattern correlation between the TRIM data and each downscale. And the added value was computed using the GPCP as a reference. So as you can see, depending on the observation data set, the pattern correlation can vary. And usually the ensemble mean outperform each individual member, but it's not always the case, as I'm going to show later. And here we show the consecutive dry days over Southern Africa as well. So again, the steepling is indicating added value. And for example, this RCA, the pattern correlation is 0.86, but the ensemble member is 0.84. So depending on the index, we can see that the ensemble mean outperforms in the individual members. Again, this is the heavy precipitation days, or rainfall, number of days of rainfall above 10 millimeters. The two observation data sets are different. For example, GPCP shows more heavy rainfall in the northern of Southern Africa, but the TRIM doesn't show that signal. And as you can see, the RCA4 is more close to the GPCP, and the CCLM is close to the TRIM. So this is to emphasize the choice of the observation data to evaluate the models. Again, the same story with the heavy precipitation days, and the maximum number of precipitation, the maximum 5-day precipitation, and the single daily intensity index. And looking at the projections, the top row shows the total annual precipitation, and this is total seasonal precipitation for September, October, November, December, January, February, March, April, May, June, July, August. So June, July, August is the dry season of Southern Africa, which is winter, and December, January, February is the wet season in Southern Africa, which is summer. And the September, October, November is the start of the rainfall season, and March, April, May is the end of rainfall season in Southern Africa. The top row is total precipitation, and the bottom row is the consecutive dry days for the RCP 8.5 at the end of the century. As you can see, in general, there's a decrease in total precipitation, but the stippling in this case indicate the changes that are not significant at 5% level. So during December, January, February, which is the rainfall season, we can say we have no change in total precipitation, but during September, October, November, we have decreases in total precipitation and increases in consecutive dry days, which means consecutive dry days increasing in September, October, November, which is the early rainfall season, start of the rainfall season, and March, April, May, which is the end of rainfall season. This means that the rainfall season is getting shorter and the total precipitation is decreasing, which might have implications for agriculture and water sector. And looking at the precipitation above, number of days with precipitation above 10 millimeters, there's not much change, but also decreasing in the early season of rainfall. And looking at the maximum 5-day precipitation, during the rainfall season, we have increasing in maximum 5-day precipitation, which means that in this region will rain a lot, and which will have implication with, for example, Mozambique, which is a downstream country. All the rivers go past Mozambique to the Indian Ocean. And looking at more extreme indexes, the precipitation intensity also during the rainfall season shows significant change increasing, and also more extreme precipitation, which means that when it rains, it will rain a lot and will have several implications. And so we got these results, and we wanted to see if these results were plausible and defensible. And to do that, these previous results that I show were submitted and published in this paper, if you are interested to know more details. So to see that if the results are plausible and defensible, we look at the circulation patterns with the aid of the self-organizing maps. And we did some first-order analysis of self-organizing maps, very simple. And just to introduce you the usual suspects that influence the weather and climate of Southern Africa. The top one, we have a winter, which is the dry season. We have much of subsidence over the continent and no rainfall, except to the western part of South Africa, which has rainfall during the winter season caused by cold fronts that usually pass by. And during summer, we have more activity, low pressures over the continent, and the high Atlantic, high Indian Ocean move southward. And we have a moisture convergence over this region, and the intertropical convergence zone goes southwards, and we have a lot of rainfall over the region over this season. So looking at the self-organizing maps, we have 20 different circulation patterns over Southern Africa. So if you look closely, we have, from bottom to top, we have cold fronts, mid-latitude cold fronts, moving up. As we move to the right, we have Indian high pressure systems, Indian high pressure system and Atlantic pressure system, which is patterns, common patterns of winter season. And in this region of the nodes 11, 14, and 16 to 19, we have patterns common of summer over Southern Africa. We have a low pressure system. So, sorry, the shaded is the area interim sea level pressure, and the arrows represent the moisture transport over the region. So we have moisture transport, and for example, here we have a convergence of moisture transport and possibly very good condition for rainfall over the region. And So these nodes, this synoptic system, they represent dry nodes. I'll show you next. And these nodes, they represent wet nodes, which means that these are conditions, these nodes show conditions of no rainfall over the region except over the western part of southern Africa due to the cold fronts that pass by during winter. So these nodes are dry nodes, and these are mostly wet nodes. And we counted the occurrence of each node for each model. So this is node 1, node 5, node 16, and 20. So these are the dry nodes, and these are the wet nodes. As you can see, for example, so this is the era interim, this is the CCLM era interim, and then this is RCA era interim, and so on. For example, if we look, the CCLM EC Earth and the RCA EC Earth. So we can see that in this case, the RCA for EC Earth overestimate the wet nodes. And I don't know if you remember, previously in the total precipitation, we see that the RCA downscaling EC Earth shows overestimated of rainfall compared to the CCLM EC Earth. And looking at the future, we can count the frequency of occurrence during this period and frequency of occurrence of this period and do the change to find out how these wet nodes and dry nodes are changing into the future. So we found that the dry nodes are increasing, and over this region, the cold fronts are decreasing, which means that rainfall over the Western Cape is reducing. And also, the dry nodes, the wet nodes for December, January, February are decreasing, except for this model, I think is an outlier, are decreasing. So the main message from this work, we found that there's added value in the GCMs, but it depends on the index being studied, and that the downscale climatology of extreme precipitation is closely with the observations. Again, also depending on the observation that you use. And the multi-model ensemble mean general outperforms any individual simulation. And for the future, we found that there's intensification of both wet and dry season, and that the dry spell is becoming longer, but precipitation may be more intense when it occurs over Central Africa. And there's a decrease in growing season days. And when we look at the circulation pattern, we found that there's increase in the occurrence of oceanic high-pressure systems, a more dominant high-pressure circulation polewards, and the decreased occurrence of continental lows and mid-latitude lows, which means that the synoptic states that reduce precipitation are increasing, and synoptic nodes and synoptic circulation that enhance precipitation are decreasing over time. And thank you.
Good. Thank you, Izidine. We have time for a couple of questions. One thing I was wondering, the SOMs, especially when they're based on sea level pressure, are focusing on synoptic scale behavior. Are there, maybe you could educate us, are there some key local features that maybe also play a role in precipitation that a SOM wouldn't capture?
Only the topographic
behavior,
yes,
in limited areas?
Yes, the few areas that we couldn't see on the SOMs.
Okay. Yeah. Any other questions? Okay, well then let's move on to our next continent. Ray Arritt is going to be talking about, I assume he's talking about North America.
Yeah.
Extreme precipitation in an ensemble of regional climate models.
Very good. Okay. Thanks, Bill, and thanks to all the organizers for the opportunity to talk with you this morning about some results that we've obtained using an ensemble of regional climate simulations to look at the incidence of heavy precipitation over the central United States. The central U.S. is an interesting region because the primary signal of climate change has really been hydrological. There's been very little warming in the surface temperature, and in fact, the warm season, April through September, surface temperatures have actually cooled slightly throughout most of the region. In contrast, we've seen a really strong increase in the frequency of very heavy precipitation, and this was quoted in our National Climate Assessment Report that you see here. In Ames, Iowa, the town where Bill and I live, in 1993, the year that I moved there, we had a 500-year flood that covered most of the town. Then 17 years later, we had another 500-year flood that you can see here that did extensive damage. We lost our drinking water for a few days because the water treatment facility was flooded out. But as you can see, the football stadium was well protected, so it was okay. When talking to the public, this really presents an opportunity for us to engage, because we can talk about warming. They may not believe warming, and in fact, they haven't seen it, and so forth. And then we say, well, can you remember when 100-year floods were more than a few years apart? And they say, oh, yeah, and that opens up an opportunity to engage with them about climate change. So this has a lot of impacts in our region because it's a heavily agricultural part of the world. It has impacts on flooding, the sorts of things it will have in most parts of the world, loss of life, failure of transportation systems, and so forth. You see that flooded out picture in the upper left. If you look closely, there is a person in that car that's in the front. Flooded fields, which cause the roots of crops to become in an anaerobic environment so that they don't grow. Field operations, you see a tractor stuck in the mud, and so forth. So heavy precipitation not only is an important climate signal, but it has a lot of impacts in our part of the world. So what we did was to construct a systematic ensemble of regional climate simulations using RCD-4. We did the CORDEX North America domain, the full domain, and covered the period 1950 through 2099. And what we're doing to evaluate the agreement with observations is to look first at a current climate period of 1971 through 2000, and then compare that to projections for 2041 through 2070. We're comparing the heavy precipitation and extreme precipitation statistics to daily measurements from the Historical Climate Network, and we have about 1,300 stations in this shaded focus region of the central U.S. that you see here. So we constructed what we called a systematic ensemble by essentially looking at variations in 3 axes. We have a horizontal grid spacing of 25 or 50 kilometers, 2 different options for convection, the Emmanuel scheme and a second scheme in RCD-4, which uses the Emmanuel parameterization over oceans and the Grell parameterization over land, and then 2 different atmosphere-ocean GCMs, which were chosen because they're relatively high equilibrium climate sensitivity, the HADGEM2 family of models, and relatively low equilibrium climate sensitivity, the GFDL collection of models. So you can see here that we can construct a 3-dimensional parameter space, and then we can look at things by holding 1 or 2 of those dimensions constant and looking at variations along the third. So first, very briefly, a broad picture of the precipitation intensity spectrum, and we see this very familiar result that the light events are over-predicted and the heavy events are under-predicted, with a crossover point of something on the order of 20 to 25 millimeters per day. So nothing too surprising there. If we look now at the difference between the HADGEM and GFDL-driven simulations, we see that the choice of GCM really doesn't have a whole lot of effect on the prediction of heavy precipitation in the current climate. You see some places where HADGEM is a little higher and some places where GFDL is a little higher, but really they're pretty well mixed with one another. At 50-kilometer grid spacing, somewhat surprisingly, we see a little bit of a tendency to predict more frequent heavy precipitation, although it's not entirely consistent. This was a little bit of a surprise to us because we expected that the finer resolution would give us more frequent heavy precipitation. And then finally, the most consistent picture is that by using the Emmanuel scheme, which are these open figures here, compared to the mixed scheme, which are the closed or the solid figures, we see that the Emmanuel scheme clearly gives more frequent heavy precipitation in the current climate. So that's going to be something to remember later on. Then if we rank the models here, we see that if we look at the most frequent heavy precipitation, those tend to be dominated by the Emmanuel scheme. The lowest ones are dominated by the mixed parameterization. There is really not a whole lot of systematic tendency along the axes of the resolution or the driving global model. So it seems to be the convective parameterization that mostly dominates this picture. Looking now at the changes, we're going to compare 2041 through 2070 to our current climate period, and these are not coincidentally the same periods that were used for the NARCAP study. So if we look at the 50-kilometer resolution spacings, we see that consistently the heavier the amount, the greater the increase. And here the current climate is the open symbols and the future climate are the filled-in symbols. And we see that all along here, and especially if you look at the higher amounts, the lowest values are associated with the current climate, the open symbols, and the higher values are associated with the future climate. We look at 25 kilometers and we see essentially the same picture. Okay, there's a little bit of detailed difference here and there, but we're not seeing a whole lot of difference in response depending on the resolution. Now, those precipitation intensity spectra have a huge amount of information in them. So to simplify this and make it a little bit easier to understand, I've just put the change in the incidence of precipitation above 100 millimeters per day here, which corresponds to that statistic I showed in one of the earlier slides. And they're organized so that I have the 50-kilometer resolution over here, the 25-kilometer resolution over here, and then within each of those, they're paired according to the driving global model. And one of the most interesting things we see here is that in each of these pairings, the mixed parameterization gives a greater increase in the frequency of heavy precipitation. The Emmanuel parameterization gives a smaller increase in heavy precipitation. So larger, smaller, larger, smaller, larger, smaller, larger, smaller. This is very consistent. This might be a little bit surprising because if you remember to a couple of minutes ago, the Emmanuel scheme gave the most frequent heavy precipitation for the current climate. And people will sometimes suppose that, well, this tends to be a wet model, so it'll give us a greater increase in the future. Well, that may not necessarily be true, looking at something like this. Clausius-Clapeyron scaling, we've seen in a couple of talks, can be useful as a way of interpreting changes in heavy precipitation. So there's a lot of statistics here, but I'll mainly draw your attention to these bottom lines here, which are the average for the 50-kilometer and 25-kilometer resolutions. And we see that for the 99th percentile, we see around a 9% increase in both cases. For the 99.9th percentile, we see around a 15% increase. And this compares reasonably well to a 17 to 18% increase that we would expect from Clausius-Clapeyron scaling. If we separate those now by the driving global model, what we see is that with the GFDL model for the 99.9th percentile, the extremes, we see about a 12.2% increase for GFDL and about an 18% increase for Hadley Center. In both cases, this starts to approach the Clausius-Clapeyron scaling, and it's also consistent with the GFDL model having a lower climate sensitivity than the Hadley Center model. So, in terms of a summary or conclusions, one of the things we see is that the GCM didn't have much of an effect on heavy precipitation incidence in the current climate, but it did affect the future climate, presumably because of the differences in equilibrium climate sensitivity. We have runs with a third GCM, kind of a middle range one in progress, that'll help to give us some confidence in these results. Again, the grid spacing didn't seem to have a big effect, which is something of a surprise to us. And then there's this contrast here that the Emmanuel scheme produced the largest frequency of heavy precipitation in the current climate, but the smallest increase when we go to the future climate, and that changes in the most extreme events are broadly consistent with Clausius-Clapeyron scaling. Future work, there's a lot of it. There's a lot of it needs to be done. There's more than we have time for, really, so we have to prioritize things. There are lots of interesting questions here, understanding some of this contradiction in the response to the parameterization. And this question I'm particularly interested in is why the finer grid spacing didn't produce more frequent heavy precipitation. Thank you. I don't know if you can see it, but this is a picture of the aurora over Stockholm. I was kind of hoping to see the aurora when I came here, but it doesn't look like it's going to work out. So thanks for your attention.
Thank you, Ray. All right, good analysis. Questions? Yes.
Hi, thank you, Raymond. Are you planning to also try to test more convective parameterizations? Because, or the point here is you have already tried with 2, but is that enough, or do you want to try to test more?
Yeah.
And what would be the objective to try to get more? Is you are going to compare with observations and try to get one, or what is the purpose for that?
Yeah, great question. We've actually done a third convective parameterization, but we haven't had time. You know, these runs produce many 4 terabyte disks full of data, and we simply haven't had time to reduce the statistics yet. So we have a third convective parameterization. We started out with all of the convective parameterizations that are available in RCD-4 and did a quick comparison using reanalysis-driven simulations, and we ranked them by performance. We're just going 1, 2, 3, all the way down the list, as many as we have time and resources to do. Yeah, that's a great point.
There's a question over there.
Thanks, Ray. Just a comment on the on this resolution issue.
Yes.
Our experience in Europe. In Europe, in ensembles, we had models at 50 and 25, including RCM. And in CORDEX, 50 and 12. And when we compared the 50 and 25, actually we didn't find big differences. Also in different metrics. But comparing 50 and 12, there were very large differences.
Yes.
In the PDFs.
Yeah.
So I'm not sure whether going around 10 or whatever is reaching some sort of threshold where the models become more sensitive. I don't know, but
yeah,
this result is kind of consistent with what we find in Europe. In fact, I remember during the ensembles days, people thought, oh, we went to 25 and we're finding more or less the same as 50. What the hell is this? Whatever. But actually, 12 really makes a very large difference. But I don't know why.
Yeah. Yeah, there's a bad echo in here, so I'm not sure that I understood all of your question. But I gather that the gist of it was that we may see more of a qualitative difference if we go down to, say, 12 kilometers, possibly. Yeah, we've wondered about that. There's, of course, a big difference between Europe and the part of the world that we're studying in, because it's a very flat region. We don't have much of a terrain signal at all, and you might expect that in Europe, once you start resolving some of the smaller scale terrain, it would make a difference. You know, there's that. There's also the question of resources. I mean, when we go from 25 to 12, it's 8 times the computing resources to do. So we've tended to put our resources into expanding the size of the parameter space rather than just, you know, we can do 8 runs at 25 kilometers instead of going down to 1 run for 12. Yeah.
One final question.
Yeah, I was going to say the same about the ensemble study, and also I want to point out the new paper by Rauscher et al. That further investigate on this issue of 50 against 25, and they try to explain a little bit of physics behind. So
yes.
Yeah, you are in line with that. And another thing I want to ask is, from our experience, the most different behavior of the model, also in terms of extreme, is when you change the land surface and not when you change the convection scheme.
Yeah.
So is this that gives you the bigger spread of the ensemble of the same model, as we shown some time ago with the CREM experiment. So have you thought in including also this third variable or fifth variable in your cubic space?
Yeah, I'm very familiar with the Rauscher paper, and I'm going to go back through and look at some of their arguments when we do some more detailed analysis of this. As far as the land surface scheme goes, we did a very large set of simulations that were reanalysis driven to try to pick out which ones we were going to go on to do the 150-year transit simulations with. And we found that, at least for this part of the world, that bats always performed better than CLM in RCM. Okay, I don't know why that is. It probably depends on where you are, the land surface feedbacks and so forth. So we decided to, because the performance with CLM was noticeably worse, we decided to just stick with bats for everything and vary the convective parameterization, because that seemed to be where most of the spread was when we looked at the reanalysis-driven simulations.
Okay, thank you, Ray. One final speaker before lunch, and I'll apologize. I'm going to make a mess of your name pronouncing it, so please correct me. Mirseid Akperov. And now we're going to be looking at some issues relating to the Arctic.
I'm Mirseid Akperov from the Institute of Atmospheric Physics, Russian Academy of Science, and I would like to present you my work, which was performed in collaboration with our colleagues from the Alfred Wegener Institute, it's Germany. Okay, aim of this work, actually there are two main tasks. First task is to assess an ability of the Arctic regional climate models to adequately reproduce the cyclone activity in the Arctic. And the second task is also to assess an ability of the Arctic regional climate models to capture polar lows. Polar lows, it's mesoscale cyclones. And I know, I suppose you know that this event is very important because they are very intensive, but had small scales, and not a lot of models can that reanalysis can capture these events. Okay. For cyclone identification, I used 6-hourly mean sea level pressure datasets from 4 reanalyses. You can see it here: ASR, RNTRM, NOSAMERA, and SubCFCR, and from ensemble of the regional climate models driven by RNTRM. This is Arctic CORDEX project for the Arctic region. And also I used polar lows characteristics from the observational data. And analysis I analyzed the analysis period was last 30 years. Here you can see in details information about models which I used in my analysis. First this is reanalysis data, and here this is regional climate models datasets. Here light colors indicate models with nudging, and cold colors indicate models without nudging. Also, I would like to note that here one reanalysis ASR and CCLM, which I used in polar lows analysis because due to their time frame, because they have short time frame. It means that I used 9 models and 11 simulations. I mean, with nudging and without nudging simulations. And briefly about methods which I used For cyclone for identification of cyclone characteristics, I used cyclone identification methods, which is based on MSLP minimum. And for polar laws analysis, I used the following procedure, which I explained on the last slide, because there will be some results from the polar laws analysis. In my analysis, I used the following, the three main characteristics, cyclone characteristics. This is cyclone's frequency. It means number of the cyclones per decade or per day. I will, independence or graph, I used a different meaning. And the second parameter, this is cyclone's depth. This is the difference between central pressure and the pressure on the left isobar in the cyclone. It's a measure of intensity of the cyclones we define here. And the third characteristic, this is radius of the cyclones. In this case, this is mean across the radius along different mean across the different radius, across different positions. Okay, on this slide you can see annual fraction of cyclone frequency, or frequency from the multimodal ensemble mean. Here, this is box plot introduction, and from three reanalysis, ERA, MERA, and CFCR. A few words about box plots. It indicates first quartile, median, and the third quartile, and the lines. These lines mean minimum value and maximum value of the distributions. And as you can see on this, in upper graph, you can see for all cyclones, and lower plots show the same distribution, but for strong cyclones. Strong cyclones we define as cyclones of a 90th percentile of the distribution, independence of their intensity, of their depths. As you can see at the top graph, there is a strong, large spread for the cold, across the models for the cold seasons, and small spread for the summer seasons. And for the deep cyclones, there is very small spread across the models. You can see on this slide. We can look also spatial distribution of cyclones frequency for the winter and for the reanalysis. This is for the ensemble from the multimodal ensemble mean, and these graphs from the multi-reanalysis ensemble mean. And you can see strong variations of the cyclone's frequency over the main cyclone activity areas, but the strongest you can see over Baffin Bay and Barents Sea for the winter season, because for the summer there is not strong variations. And on the left slide you can see tailored diagrams for the winter and for the summer for the cyclone's frequency. And here you can also see that in the winter we have a large spread in variations of cyclones frequency with respect to the summer. And I would like to note that these cyclones possibly the nature of these cyclones is a combination of the orographic and barochronic effects. And for this area, Barents Sea, there is this variation may be related with the representation of the polar laws, which is dominate over these areas. Just few slides which I would like briefly, shortly describe. This is a special distribution of cyclones mean depths. I would like to indicate that all models quite well reproduce these characteristics for the winter and for the summer. And the same graphs, but for cyclone mean size, it's the same situation. You can see that for the winter and for the summer, all models can well represent this characteristic. And about cyclones here, about distribution, independence of the cyclone depth and size. Here you can see that large spread or strong variations you can observe for the small cyclones. For the small cyclones and for the cold season. As I indicated before, it can be related with the small cyclones like polar lows, which have small scales and also they have short lifetime and for summer we don't have any large. We had spreads, but this is much smaller than in cold season. And here we looked trend estimates for from all models and reanalysis. First three, this is reanalysis, and other, this is models. For the all cyclones and for the deep cyclones. I would like to note that for the summer, all models show the same trend as in the all reanalysis, but for the winter there are different signs of the trends and amplitude. But for deep cyclones, in general, we have the same behavior. I forgot to say that this is trends for the cyclones frequency. And last slide, it shows how well data sets, reanalysis and models can represent polar laws. Here, as I indicated, as I mentioned above, we compared polar laws. We compared the polar laws from the observation data, and using procedure, which I mentioned above, we tried to select the correspondent cyclones in the all models, and found that not all models can represent well polar laws in models. And this is percentage. Reanalysis can represent about 60% of observational polar laws, and first 4, this is reanalysis, and other, this is models. And models can represent from 25 up to 60% of the real polar laws. And conclusions. Some of the regional climate models with nudging show better agreement in representing cyclone characteristics, including polar laws, compared to other models with and without nudging. And strong variation in cyclone frequency across models and reanalysis are observed in winter and for small cyclones. And possible reason it's polar laws, which and the third conclusion is the state-of-the-art Arctic RCMs can resolve about 60% of polar laws. Thank you very much. That's all.
Thank you. Thank you, Mirseid. Time for a question or two.
Yeah, sorry, this is more like a curious question, but do you know how the grid is represented close to the North Pole in these RCMs that work with the GCMs? I don't understand that issue, but how is the grid represented there, close to the North Pole? Because it seems for the GCMs, at least the regular ones, should have a lot of points close to the North Pole, right? So how is the grid represented in an RCM there? Probably it's not, I don't know, somebody knows?
Sorry, but I think he's talking, you're talking about the resolution?
Yeah, about the grid itself.
How's the grid resolve things? It's fairly uniform, isn't it?
Sorry?
The grid at an RCM going over the North Pole, the resolution, it doesn't change.
Yeah, it doesn't change.
Doesn't.
No, they had the same resolution.
Yeah.
I mean, in terms of spatial resolution.
Yeah.
Just
yeah, it's not going to. Oh. It, the same. It stays the same. Yeah.
Yeah. I rotated. I interpolated to the.
You had okay.
Yeah. All the data were interpolated.
Okay. No, good. Okay, I want to thank all the speakers again this second session for keeping on time and giving very interesting presentations.